Look up at the night sky. It's dark, simple, obvious meanness, and actually a paradox. The observable universe holds roughly 70 sextillion stars. If space stretched on forever, every single line of sight from your eyes would eventually land on one. The night sky shouldn't be dim, it should be as bright as the surface of the sun, in every direction, all at once. That's a real paradox with a name. And here's the part that should embarrass every physicist. It was solved not by a cosmologist, but by Edgar Allan Poe in a prose poem in 1848. He figured out the universe is too young for all that light to have reached us yet. And that is the most straightforward paradox on this list. Because what comes next will shatter causality, erase information from existence, and force you to ask whether you finest right now are even a real person or just a freak accident in an infinite void. Let's go. Start with the dark sky, because it has a longer history than you'd think. Johannes Kepler noticed the problem back in 1610, and he used it as a weapon, an argument that the universe simply could not be infinite, or the whole sky would burn. Cosmologists mostly shrugged and moved on for 2 centuries. Then, in 1823, the German astronomer Heinrich Olbers formalized it in a treatise written in Bremen, and his name stuck to it. Olbers Paradox. Poe cracked the idea in 1848, writing that the background of stars is so unimaginably distant that no ray from it has managed to reach us yet. Lord Kelvin turned that intuition into real mathematics in a barely read 1901 paper. And then, in 1964, the cosmologist Edward Harrison solved it all over again, with no idea that Kelvin and a horror writer had beaten him to it. The modern answer has 2 halves. 1. The universe is only about 13.8 billion years old, so there simply hasn't been time for distant starlight to arrive. 2. The universe is expanding, and that expansion stretches the light of the most distant sources right out of the visible spectrum, redshifting it down into faint, invisible wavelengths your eyes can't register. The blaze Kepler feared is real. It's just been stretched into colors you'll never see. Now speed up. Einstein, 1905, in the paper that founded special relativity, made a quiet little note: take 2 synchronized clocks, send one on a journey, bring it home, and it will read behind the one that stayed. That footnote grew into the twin paradox. Picture identical twins. One blasts off at near light speed, the other stays on Earth. Here's the knot. Motion is relative, so each twin sees the other's clock ticking slow. Each one should think the other is younger. They can't both be right. The resolution is that the situation isn't actually symmetric. The traveling twin has to slow down, turn around, and accelerate back real, felt forces the stay-at-home twin never experiences. That broken symmetry settles it. The traveler comes home genuinely younger. And we have tested this with actual twins. NASA's twin study sent astronaut Scott Kelly to the space station for 340 straight days, from March 2015 to March 2016, screaming around Earth at about 17,500 miles per hour, while his identical brother Mark stayed home. Over the whole mission, Scott aged roughly 5 milliseconds less. As Mark put it, where he used to be just 6 minutes older, now he's 6 minutes and 5 milliseconds older. Relativity, measured between 2 brothers. We leave the everyday behind. There's a faint radiation bathing the entire sky, the afterglow of the Big Bang itself, released when the universe was only a few 100,000 years old. We call it the cosmic microwave background. Map its temperature across the whole sky, and it is smooth to 1 part in 100,000. Astonishingly uniform. Here's why that's a problem. Take 2 patches of sky on exact opposite sides of the universe. In the time since the Big Bang, light has never had time to travel from one to the other. They have never been in contact. Nothing has passed between them. So how did they end up at precisely the same temperature? Regions that have never touched, never exchanged so much as a photon, somehow agreed on the conditions down to 5 decimal places. That's the horizon paradox, and the leading answer is a violent one. A fraction of a second after the Big Bang, the universe may have expanded exponentially, faster than light, meanness, from a tiny patch that had already evened out. Everything we see was once in contact, then flung apart. If true, the whole cosmos is a single, stretched-out echo of one microscopic region. That same idea patches a second wound, and this one is about geometry. The overall curvature of the universe is measured by a number cosmologists call omega. If it's above 1, space curves in on itself and collapses. Below 1, it flies apart too fast to build anything, and the measured value sits at essentially 1.0000 flat to a razor's edge. The trouble is that flatness is unstable. In the early universe, the tiniest deviation from perfectly flat would have exploded into a wildly curved cosmos within moments. For it to look this flat today, the early universe had to be balanced on a knife's edge with impossible precision. No dial in nature likes to sit at exactly 1 for no reason. That's the flatness paradox, and again, inflation is the escape hatch, because stretching any surface enormously makes it look flat, the way a beach ball blown up to the size of a planet feels like level ground under your feet. Now, the one physicists say out loud is the most embarrassing number in all of science. Quantum field theory says empty space isn't empty. The vacuum churns with energy, particles flickering in and out of existence everywhere all the time. So you can calculate how much energy should be packed into nothing at allness, and that energy should drive the expansion of the universe. We can also measure the real thing. We call it dark energy, and it's out there, gently accelerating the cosmos. So you compare the prediction to the measurement, and the theory overshoots reality by a factor of 10 to the power of 120. That's a 1 followed by 120 zeros. It is, by a wide margin, the worst quantitative prediction ever made by a serious physical theory amenus, and nobody knows why the number is so catastrophically, precisely wrong. Take a breath, because the next one is hiding in your kitchen. Drop an egg, it breaks. It never unbreaks. Stir milk into coffee, it never separates back out. Time runs one way. But here's the disturbing part. Almost every fundamental equation in physics works exactly the same forwards and backwards. At the level of particles, the laws don't care which way time flows. So where does the arrow come from? The answer is entropy, the second law of thermodynamics, which says disorder always increases. But that just relocates the mystery, because for entropy to keep climbing, it had to start incredibly low. The Big Bang had to begin in a state of staggeringly perfect order, and no one can fully say why. The reason you can't unbreak the egg traces all the way back to the initial conditions of the universe itself. If time is strange going forward, it's lethal going backward. Einstein's own field equations contain valid solutions called closed time-like curves paths through spacetime that loop back to their own past. Take one seriously, and you get the grandfather paradox. Travel back, stop your grandfather from ever meeting your grandmother, and you're never born, so you never travel back, so he's fine, so you are born. The logic eats itself. And this isn't just a movie plot, it's baked into the mathematics of general relativity, which physics has otherwise confirmed to spectacular precision. Either something we don't yet understand forbids those loops from ever forming, or the universe enforces a strict self-consistency that only permits journeys which never change anything. We genuinely do not know which. Now a crack that's splitting modern cosmology in real time. There's a number called the Hubble constant that tells you how fast the universe is expanding. Measure it one way Mygonus by reading that ancient microwave glow from the early cosmos Mygonus, and you get about 67.4 kilometers per second per megaparsec. Measure it another way Mygonus by climbing a ladder of nearby stars and exploding suns out into the present-day universe Mygonus, and you get about 73. Those two numbers should be identical. They are not. And the gap has hardened into a 5 sigma discrepancy, the statistical threshold physicists treat as a real, undeniable signal. In any other field, a gap that stubborn would have ended careers and rewritten textbooks minus here, it just keeps growing. It refuses to shrink as measurements get sharper. Two honest methods, two different expansion rates, as if the early universe and the late universe disagree about how fast they're growing. Something in our picture of the cosmos is broken, and nobody has found it yet. And now the paradox that questions whether you exist. In an infinite, eternal universe, random fluctuations never stop. And anything that can assemble itself by chance, given enough time, eventually will. Ludwig Boltzmann's statistical mechanics forces an unsettling conclusion. It is vastly, overwhelmingly easier for random fluctuations to conjure a single conscious brain, complete with a lifetime of false memories, than to build an entire orderly universe of galaxies and planets. So in a cosmos like that, the typical observer isn't a person on a world, it's a lone brain, flickering into being in the dark, thinking exactly your thoughts, and dissolving. The paradox is that our best theories don't rule this out, and if they predict that most observers are these fluctuations, then statistically you should be one. The fact that you seem to live in a stable, sensible universe is a clue that something in our cosmology is still wrong. Which finally brings us back to the stars. Summer, 1950, a lunch table at Los Alamos National Laboratory in New Mexico. Enrico Fermi, talking over lunch with colleagues, suddenly asked out loud, "But where is everybody?" Think about what's behind the question. The Milky Way holds 2 to 400 billion stars. The observable universe, 76 trillion. Even cautious estimates suggest millions of potentially habitable worlds in our galaxy alone. In 1961, the astronomer Frank Drake chalked up an equation to organize a conference agenda, a way to estimate how many civilizations we might hear from. The attendees guessed about one new star forming per year and nearly every star hosting planets, and modern data has proven them right within a factor of 2 or 3. So the galaxy should be crowded, the sky should be noisy. Instead, silence. In 1996, the economist Robin Hanson gave the silence a chilling name, the Great Filter. Some barrier makes the leap from lifeless rock to spacefaring civilization almost impossible, and the terrifying question is where that filter sits. If it's behind us, we're the lucky ones who made it through. If it's ahead of us, then finding the ruins of a dead alien civilization would be the worst news humanity could ever receive. And now the climax: physics at war with itself. In 1972, Jacob Bekenstein claimed black holes have entropy proportional to the area of their event horizon. He was ridiculed because entropy means temperature, and temperature means the thing must radiate and nothing escapes a black hole. Then in 1974, Stephen Hawking published in Nature and proved Bekenstein right. Black holes glow. They leak thermal radiation and, over eons, evaporate. But that radiation depends only on the hole's mass, spin, and charge meanness, which means everything that ever fell in, every book, every star, every person, is erased. And quantum mechanics flatly forbids information from ever being destroyed. That's the contradiction. It gets sharper. A 10 solar mass black hole has a temperature of 6 billionths of a degree above absolute zero minus 400 million times colder than that microwave glow minus, so it can't even evaporate yet, and complete evaporation would take 10 to the 67th power years. A group of theorists showed that saving quantum mechanics would turn the event horizon into a wall of lethal radiation, save one law, break the other. A newer approach, using wormhole geometry, suggests information does escape after all minus, but the full proof isn't in yet. It's the best answer we have. It is not the final one. So look up one more time. That dark, quiet sky, the paradox Poe solved with a poem, turns out to be the shallowest layer of something far stranger. A few of these puzzles are truly solved. Most are open wounds, the flatness, the constant, the tension, the information. And that's the thrilling part. Every one of those unresolved paradoxes is a door minus, and behind one of them is the next revolution in physics, waiting for someone to walk through. This has been Cosmic Doodles Minus, and the sky is a lot weirder than it looks.